All right, guys, let's talk through 2.6, resonance and formal charge. All right, we just talked about resonance in the last video, so hopefully you watched and you saw a couple extra examples of how to do Lewis structures. So we talked about resonance, and resonance, remember, is a pi bonds, so double and triple bonds, and they are moving between equivalent places in the Lewis structure. And what we found in the last video is that instead of having a single and a double bond, the actual data shows us that we have somewhere in between a hybrid bond of a single and a double bond. And so the example here on the right shows that if we have blue and yellow and we put those together, we make green. And that's kind of what our resonance structure does. And so you can see this O3 molecule. It has a single and a double bond, just like our nitrite did in the last video. And what you notice about the ozone is that it has the same bond length in it. Okay, and so it's symmetrical across the entire molecule. And that's because the resonance, the electrons are moving in such a way that it's a blend of two. Okay, so our electron density is distributed symmetrically across all of the bonds. All right, one of the best examples of resonance is the organic compound benzene, C6H6, and it has two resonance structures. And so what you notice is it is depicted normally as a hexagon, so a six-sided ring, and every other carbon has a double bond. And so if you notice your double bonds here and here and here, that's not a very good color. And then you notice that they move to here and here and here. All right, and so this would be considered a resonance. And these are called delocalized electrons. So again, when you look at the hexagon, the electron density is split equally between all of those carbons. We don't have the length of a single bond and the length of a double bond, which would be shorter, but we have somewhere in between both of those lengths. And that's because those electrons really are acting almost like a sea of electrons where they can move around like in a metal. They're delocalized electrons. Okay, so delocalized electrons. Now, one thing to note is that in organic chemistry, I will tell you that chemists are lazy. And so if you notice here, what we have is we have our carbons at each corner of the ring. And so one thing you will notice is that most chemists will not draw it like that. You will actually draw it here with just the ring structure. So just the six-sided ring. You won't put in the carbons and you won't put in the hydrogens, because by putting in the single and the double bonds, it's telling you that at each corner there has to be 4 bonds. So there's a carbon at the intersection, a hydrogen out at each one. And this is understood in organic chemistry. Most of the time you do not write your carbons and your hydrogens. It's just known that they're there. Okay? And so that's another way to write that same ring. Okay, and so you'll notice this is the shorthand way. And then when you get even lazier, because these are delocalized electrons, a lot of times people will draw this just the circle, saying that these electrons are really rotating among all 6 carbons equally. Okay, and that's another example of resonance. All right, so all resonance structures are present simultaneously. They don't flip between the structures. Okay, so we think of them as kind of flipping back and forth, almost like those flip books that you see, that you used to see. You draw pictures a little bit slightly different. You flip through them and it looks like maybe the person is moving or running. Okay, that's not really what's happening. These delocalized electrons are essentially just everywhere, and they are giving the bond lengths as an average. Okay, so again, we don't have a single bond and a double bond length. What we do have is we have an average of the two, a hybrid of the two. And in my last example, we did look at nitrate already. This is another way to show resonance, is to put a dotted line where the double bond would be, because it is showing that that double bond is moving between the two locations. All right, the next thing we need to talk about is formal charge. Okay, so formal charge is the charge an atom would have if all of the electrons in a covalent bond were shared equally. Formal charges should add up to the overall charge of the atom or the ion. And so for a molecule that is neutral, that should be 0. For an ion, that would be the charge of -1, +1, -2, +2. Okay, so it would be whatever the charge is. The best Lewis structure is determined by the formal charge of each atom. The best formal charge to have on an atom is the closest you can get to 0. Okay, and negative charges go on the most electronegative atom. Okay, so give me a second here, and I am going to flip back because I've added some slides to talk more about formal charge that I think make it a little bit clearer. All right, so again, formal charge, the actual calculation is the number of valence electrons minus the non-bonding electrons minus half of the bonding electrons. Okay, the other thing you can think of is the valence electrons, and it would be minus the electrons assigned. Okay, and when you subtract those two numbers, then you get your formal charge. So it doesn't really matter how you think of it. And the electrons assigned are these electrons. So we know our lone pairs are assigned totally to the atom, and then they are sharing any bonding atoms. So it's the amount of electrons in a specific atom when the molecule shares the electrons equally. This only applies to covalent molecules, okay? Only applies to covalent molecules. So if we look at these examples down here, this one is the nitrate ion. It says, what is the formal charge of nitrogen? And so if we take a look, nitrogen is in group 15, so it has 5 valence electrons. Right now it doesn't have any lone pairs, so that's 0. And minus half of its bonding. So its bonding electrons are 2, 4, 6, 8. So half of 8, which would be 4. So 5 minus 4, and the formal charge on this nitrogen is a +1. Okay, we know a nitrate ion has a -1 charge. Okay, so this right here is going to be a -1 charge, and that is because of the oxygens. So let's take a look at the oxygens. So we know that these oxygens here on the bottom have 6 valence electrons. They have 2, 4, 6 electrons that are lone pairs, and they have 2 bonding electrons, so half of that is 1. So for this oxygen on the right, we have 6 minus 6 is 0, minus 1, this is a -1 charge. Okay, so this guy has a -1 charge. This one's also going to have a -1 charge because it is equivalent on the other side. Now let's look at the oxygen up at the top. It's going to have its 6 valence electrons. Right now it has 2, 4 lone pair. And then it has 2, 4 bonding, but we only use half of that. Okay, so this oxygen would be 6 minus 4 minus 2. It has a formal charge of 0. Okay, so then if we add up all the formal charges, we have a +1, a -1, which is 0, plus 0, plus a -1, that gives us the overall charge. All right, let's look over here at the other one. This is the cyanide ion. So it says, what is the formal charge of the carbon? Okay, so we look at the carbon here. It has 4 valence electrons, minus 2 lone pair, minus half of the bonding electrons, and it's a triple bond. And so we are going to count half of 6, which is 3, and it has a formal charge of -1. Let's look at the nitrogen. Okay, the nitrogen has 5 valence electrons. It has 2 lone pair, that will be by itself, and it is sharing the 6 bonded electrons, which is 3. Half of that is 3. And so the nitrogen has a formal charge of 0. So the carbon has a formal charge of -1. The nitrogen has a formal charge of 0, and that's what gives us the overall charge of the atom. All right, so if we're talking about formal charges, where the good-bad range is, 0 formal charge on any atom is the best. It's fine if you have a +1 or a -1. A -1 is good, especially if it's an electronegative atom. If you start getting into the -2, -3, or +2, +3 range, that is a formal charge that is not the best Lewis structure. So as you're looking at the Lewis structure, you would want to go ahead and come up with a different Lewis structure. And again, our negatives here should be on the most electronegative atom. Okay, so the most electronegative atom should have the negative charges because it can pull the electron density towards it. All right, so it says draw 3 possible Lewis structures for the cyanate ion, CNO, where C is the central atom. Okay, then calculate the formal charges of all the atoms in each structure and determine the most stable for the ion. All right, so we have our carbon, which has 4. We have our nitrogen, which has 5. Our oxygen has 6. So we have 15 valence electrons plus this -1. So we're going to add 1 to it. So we're working with 16 valence electrons. Said that carbon has to be the center. Okay, so let's see what we can work with. And again, I'm just going to pop in my brackets in my chart just so I don't forget it. So 16, I've used 2 to make a bond. So I'm going to go with 2, 4, 6, 8, 10, 12, 14, 16. Okay, so obviously I am going to need to do something better than that, right? So I'm going to take one of those pairs of electrons away, and I'm going to swing it in here. So I have 2, 4, 6, 8, 10, 12, 14, 16. All right, so that is a Lewis structure. Notice the carbon doesn't have enough right now. And so I'm going to take one more. And I always erase half of my atom when I do that. I need to get better. And I'm going to put in a triple bond. All right, so this is my first Lewis structure. I've used 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons. My nitrogen has 5. It has 2 lone pair, and it is sharing half of the 6 bonding, so 3. It has a formal charge of 0. My carbon has 4 valence electrons. It has 0 lone, and it has 2, 4, 6, 8 bonding. Half of that is 4. It has a formal charge of 0. My oxygen has 6 valence. It has 2, 4, 6 lone pair, and half of 1 bond, which is 1. So this is a -1. So right now, I have 2 of my atoms at a 0 and my most electronegative atom with a charge. So this is a winner-winner chicken dinner right here. Let's look at a different one and see if we could come up with something else. So what happens if we had a double bond on that side? Okay, so maybe we had a double bond on each. Double bond, 2, 4, 6, 8, 10, 12, 14, 16. Okay, let's check this out and see what happens. Nitrogen, again, is going to have 5. It now has 4 lone pairs, and 2, 4, half of that is 2. And so we have a -1 charge. Okay, it's not terrible because nitrogen is more electronegative than our carbon is, so that could work. If we look at our oxygen, we have 6 minus 4 lone pair minus 2, 4, 6, 8. Half of that is 4. So we have a -2 charge here, a -2 charge. Okay, a -2 charge isn't great in that situation, right? And then if we look at our 2, 4, 6, 8. Oh, this was a mistake right here. So we have 2, 4. This should actually be a 2 right here. Oh, it actually worked when I scribbled that time. Okay, so we have a 2. And this would be actually a 0 charge. Sorry for that mistake. All right, so we have our -1, our 0, and carbon is the same as the other one, and it would have a 0. So again, we still have a -1 charge, but in this structure, our -1 is on nitrogen, which is less electronegative than our oxygen. So again, our one with the triple bond still is better. Okay, and then you could do one where you put the triple bond over with the oxygen, okay, and calculate that. So you can see that formal charge helps you determine the best Lewis structure that you can write. All right, so let's go back down to here. Okay, so carbon dioxide could have 2 different Lewis structures. It could have carbon with 2 double bonds, or it can have a carbon with 1 single and 1 triple bond. And you should figure out the Lewis structure to try to figure out what is the best. So if we're going to look here for this guy, we're going to have our oxygens. Oxygens have 6 valence electrons, 2, 4 lone pair, minus 2, 4 bonding, and half of that is 2. So that is 0. So this is our oxygens. Both oxygens have a 0 formal charge. Then we look at our carbon. We have 4. There are 0 lone pair. And 2, 4, 6, 8. Half of that is 4. And it's 0. Okay, so we have a 0 formal charge here, a 0 formal charge there, and a 0 formal charge, which you can't see very well on the white. If we go over to the one on the left, our oxygen, and I'm going to say oxygen on the left, has 6 minus 6 minus half of the bonding, which is a -1. Now this isn't a terrible formal charge for oxygen because it's electronegative. Let's look at our carbon. Carbon has 4. It currently has 0 lone pair, and 2, 4, 6, 8. Half of that is 4. And that is 0. Okay, and then our oxygen, let's say oxygen on the right, has 6 minus 2 lone pair, minus 2, 4, 6. Half of that is 3. And it has a +1 charge. Okay, so now we're looking at a -1, a 0, and a +1. Now we still have an overall charge of 0, but again, we have a positive charge on an electronegative atom, okay, which is not the best Lewis structure for that. Okay, and we went through this already. Now, there are times where you can have exceptions to octets. So there are 3 types of ions or molecules that do not follow the octet rule. So ions are molecules with an odd number of electrons. Okay, odd numbers of electrons. They are rare and usually called free radicals. Okay, so when we think of things that are causing havoc in our atmosphere, usually we have free radicals doing that. They are highly reactive because they have that 1 electron. Ions are molecules with less than an octet. Okay, you don't see things that have less than an octet that often. Obviously, we know our normal exception of hydrogen and helium, which only need 2 electrons. But you can also see things sometimes like boron. So something like BH3. BH3 has less than an octet. And why because it actually will be a Lewis acid base pair with NH3. So because it has less than an octet, and then something like nitrogen has an extra set of electrons, then boron, when it has less, can actually make a bond with that, okay? And so things like BH3 usually end up making some sort of Lewis acid base pair or a complex ion. And then we have ions or molecules with more than 8 valence electrons. Remember, and those were our expanded octets. Okay, and our expanded octets, we talked about, they are in period 3 and below because they have the availability of D electrons. Okay, most of the time you see them with sulfur, you see them with phosphorus, you see them with the bottom of the noble gases. Okay, so we see here an exception to the octet. We have a free radical here. We have, again, boron. Boron tends to have less than an octet. When you look at its Lewis structure and then you check the formal charges, you're going to find that it actually is better when it has just less than an octet. Okay, so again, boron is much better here than when you try to give it a double bond. And then we have our expanded octets here. Our expanded octets, and again, it's because they have more electrons than the 8 in the octet, and they have D electrons that can do that. So in periods 3 through 6, they use the D orbitals to make more than 4 bonds and become hypervalent. Okay, and you can go through the practice problems.